So today we are starting another lecture, lecture 48, and this is going to be primarily about some of the limitations of response surface method and some of the methods beside polynomials which can be used for surrogate modeling. And again, I am Dr. Ranjan Ganguly. Now, one of the issues in response surface method is that as the number of design variables increases, the number of runs becomes progressively larger. Essentially, you have to run your experiment or simulation at a plethora of points as the number of design variables goes up. And this is sometimes known as a curse of dimensionality, in that as the dimensions of the problem become large, that is the value of k becomes large, the problem becomes intractable. So we can see some aspects of this in the CCD if we are trying to develop a quadratic response surface. And here I have given several values of the factor k, and then we have also given the number of regression coefficients here and number of runs. So you can clearly see that as the value of k goes up, the number of regression coefficients does go up, but the number of runs increases dramatically. And for example, if you had 10 design variables, you would have 66 regression coefficients, but you have 1045 runs, which would be extremely large and would cause problems for most people. So one of the good points about CCD is that the number of design runs is always greater than the number of regression coefficients. So on the positive side, you do get a plethora of points and you can fit a very good response surface through these points. But we also see from the previous table that most of the runs come from the 2k design, that is 2 to the power k design. And because this power is here, if k becomes large, this becomes extremely large. So essentially the factorial points are going to dictate the points which are dominating the runs. So this is something which is a problem for CCD as the number of design variables becomes large. So this particular problem becomes extremely difficult to resolve when your number of design variables becomes greater than 15. And in many cases, you will see that most response surface methods are being used for problem sizes which are relatively less, which are less than 15. And this is something which is tractable by typical engineers working in companies and different organizations. However, if there are PhD students working on a problem, they may sometimes have the time to consider larger dimensions for the problem because they have considerable time to do these runs, but in most realistic cases it becomes problematic. But we can say that if you have a problem with 10 design variables or less, response surface method is a very good approach. And one of the strengths about this method is that it essentially decouples the analysis problem and the optimization problem. And this is particularly important in the company or industry setting where large computer codes are routinely used for calculation. So these codes may be based on computational fluid dynamics or structural methods and so on. Now it's very difficult to make changes inside these analysis code because they may be developed by some research group in the company, or they may also be bought from different vendors, in which case you may not have the possibility of changing these computer codes. Therefore, you cannot go inside the code and try to put in your optimization code if you wanted to, which is sometimes possible in a setting such as a university where a student is working on a PhD problem. So generally it is hard to combine the codes which are there for the analysis with the different codes which are there for the optimization. And this problem is largely resolved by the use of response surface methods. So we can imagine a situation where there is a company and maybe it's developing something such as a flight vehicle or a vehicle, in which case you may have different analysis groups, you may have a different structures group, a fluid mechanics group, and so on. And each group can develop a response surface for a specific cost function with respect to the design variable. And then there may be some people who have expertise in optimization who combine all these response surfaces and come up with an optimization problem which they can then solve. Now, this response surface type of thinking has been used by not only a company with many groups, but also by different research labs and companies working on a particular project. And this is especially true when a very large system level project is being made. And then there are different groups who have different expertise, and these groups may in fact be located in different countries or different states. So again, there is this important field called MDO, multidisciplinary design optimization, which essentially looks at problems where the objective functions and constraints come from different disciplines. So they may be coming from structures or fluid mechanics or control or propulsion if we are looking at a typical vehicle system, or in a different system they again may come from various sources. So again, response surface methods are useful in solving these kind of MDO problems because different people can develop different functions and they can be combined together. Now, one more advantage we have seen before is that the use of polynomials lets us use many different type of optimization methods, and we can even use KKT condition to find the solution of many problems. And again, both the objectives and constraints can be expressed in terms of response surfaces and the problem can be solved. Now, we also saw that it's best to keep the response surfaces to within small regions of the baseline design and then move using sequential CCD through the design space. Now, sometime you may use some tricks. For example, you may actually start off with a rougher design. You could use a 2-level factorial to start the process. You could enhance it by a center point. And then as you slowly move toward a region which is more likely to be the region where your minimum point is there, you can switch to quadratic response surfaces with CCD. So various permutations and combinations are possible in response surface method, and it particularly depends on the user who is developing this problem and also the domain knowledge of the user about the problem. Now, most optimization books do not discuss response surface methods in detail, but there is a book on this topic by Montgomery and Myers, which is a textbook on this subject. It is not really focused on optimization, but more towards the design of experiments approach or quality approach, but it's a very good reading if somebody is interested in response surface methods. Now, in recent years, various new meta models have come up, such as Kriging, which is also known as Gaussian processes, and these methods try to capture a global approximation to the problem. So instead of doing local modeling, they try to do a global modeling for the complete problem. Neural networks are one more method which has been developed, and they are also good global models. Global models are useful if you have a complicated nonlinear function with many local minimum point and you want to zoom into the best local minimum point. However, I would say that polynomial response surfaces are well suited to most engineering problems because a very deep local minima is often not very useful. You want a shallow local minima which is robust. That means if you have perturbations in your design variable, your minimum point should not fluctuate too much. So response surfaces based on polynomial do help you in these kind of situations, and you get good robust optimum design. And we have seen this in a work where we compared neural networks with response surfaces and found that response surfaces actually did give a more robust design, though neural networks gave a greater reduction in the particular objective function we were dealing with. But the neural network may lead you to a deep local minimum point, which again may be too sensitive to any perturbations in the design variable. So I will stop this lecture here. I will see you in my next video.